So, hello everyone. Good evening for the people who are closer to the Singapore time frame, and good morning for the rest of the world who are closer to the United States time frame. So it's pretty much early here. My name is Amin Gharehyakheh. I have a PhD from in the industrial engineering, and I recently graduated from the University of Texas at Arlington. So I will talk about waste management in perishable food distribution, part of my PhD research in University of Texas at Arlington. And I will be happy to present it for the Summit of Recycling and Waste Management 2020. So at first, we want to talk about why food waste management is so important. So economically, we have about 40% of the food produced in the US thrown away, and it costs us annually $750 billion globally, which is basically accounts for the 1.6 billion tons of food in waste. So it's a huge and big number. But it's not only the economic impact. It also have environmental impact. So 21% of the landfills are food waste. Food waste is the largest component of the landfill municipal solid waste in the U.S. and it accounts for 18% of the methane emissions in the U.S. So also, if you want to see it from the food insecurity point of view, in the United States, about 1 in 7% are food insecure. It means that they don't know if they have enough food or what will be their next meal in their for their lunch or dinner. So basically, we are dealing with different type of problem if we have food waste in the system. We have 21% of the waste of landfill are including food waste. 40% of the food are thrown away in the US. 1 in 7 people are food insecure, and it accounts the food that's been thrown away. Imagine if we have the family of 4 persons, it's about 1500 for a year for family of 4, and it's a big number if we consider it globally. So what actually is happening in the food system which is causing food to be wasted? So the main impactful item is temperature. As we know, and we are familiar, we want to keep the food in the desired temperature level to be sure that the quality degradation will be on the minimum level. So let me describe here what it does mean in the point of view of organism inside the food. So basically, there is one specific spoilage organism, SSOs, which accounts for the food spoilage in the food products. So the amount of SSOs will start with some initial level, and it will follow some lag phase and exponential phase, and then it will reach to a stationary point. So at the time that it passes the maximum acceptable level, the food is not safe to use, and after that level, it's wasted. So basically, we have here on the right-hand side 3 different colors, which is basically showing the growth of number of SSOs inside food products, and on the blue one accounts for the lowest temperature that we are keeping this product, and it shows that it will have the highest shelf life. And if we increase the temperature, the lag and exponential phase of growth will be faster, and it will reach the maximum acceptable level even sooner. So if we achieve this number, maximum acceptable level, sooner, it accounts for the lower shelf life. So our goal is to keep the temperature at the desired level as much as possible. So, but what is happening inside the container of the refrigerated vehicles when we want to deliver a demand for the customers? So refrigerated vehicles are responsible to uh, load the products, food products at the depot, and deliver it to the maybe more than even in some cases 20 or 30 customers, because nowadays the size of orders are most of the time are less than truckload, and if you want to deliver economically the demand to the customer, it totally makes sense to aggregate all of them into one vehicle and deliver it to multiple locations. But the thing, if you see this right-hand side graph, the temperature inside the container will fluctuate when every time that we want to unload part of the cargo in the customer location. The heat inside the ambient heat will transfer by blowing hot air inside the container, and it will cause some fluctuations in the temperature inside the container. And if we go if we go forward from the first customer to the last one, this fluctuation will be wider. The reason is the mass of the products that we have inside the container will get lower and lower, and basically for the last customer, most of the products are gone, and the hot temperature will hot air will cause lower mass of products to have its temperature increased. So the fluctuation will be wider and wider inside the containers the container temperature. So it's a big deal for us. And we, in this research, the main goal was how we can predict the temperature before even leaving the depot and having the actual distribution. So the thing that we did is we used energy balance equations. We calculated the amount of energy that every time that is coming inside the container when we are unloading part of the cargo at a location, for example, at location J. So the temperature increase after doing this, the mass and simplifying the equation will be equal to the first equation in here. And but at the second time, when after leaving the location and the container door is closed, the actual cooling equipment will capture this increase in the temperature, and it understands that it's higher than the desired level. It starts blowing the cold air inside the container, and which basically for the purpose of absorbing the amount of heat that came into the container. And so if we say we are between node I and J of delivery, the temperature between node I and J is equal to this equation. Basically, it is the capacity of cooling equipment divided by the body mass that of air and the cargo inside the container, multiplied to the duration of time that we are between node I and J, plus the T0. T0 is the temperature that container has before at the time that it left the node I. So it will show some sort of decline in the temperature, but this decline, as I showed in the previous slide, will be like going down, but how much this decline is acceptable. So we have this desired temperature, and when it reaches this desired temperature, the thermostat will shut off the cooling equipment. So basically, the temperature between node I and J will be the maximum of the temperature which has been predicted during the transportation phase, and the desired temperature which has been set for the thermostat of the cooling equipment. So if we have this temperature prediction for the distribution plan even before leaving the depot. So we can use some shelf life prediction models. In this case, we use Arrhenius equation and Gompertz model at the same time to predict the shelf life of a product, or if I want to say it with the exact terminology, number of SSOs that I talked earlier. So Gompertz model will tell us how number of SSOs will grow based on the this formula at the based on the second formula that's here, and the Arrhenius equation will show the effect of temperature on a speed of growth of SSO counts. So basically, if we have one solid temperature, it will follow on the shape of the right-hand side picture. But if the temperature grows, the slope of this curve will be higher, and it will reach the maximum acceptable level sooner. So now we want to be sure that how we are gonna interpret this quality loss in our plan. Now we know that we have this temperature prediction. We know that we can use it to estimate the food quality and shelf life of a product. So what does food quality mean for the distribution plan? So in the literature on the left-hand side, mostly they are talking about the effective quality and visible quality, basically without considering the effect of temperature. They are considering the one linear decline on the quality of products through the time, but it will be a time that customers or consumer will not see any sort of visual changes in the quality of product. Let's say you are going to a supermarket, you will see a product with a good shape, with a good odor, and you will say, okay, I'm gonna buy it and I'm gonna pay the full price for this one. But sometimes you will see products that are not in a good shape, so you are not so eager to pay the full price for this product. So this is the point that they call it quality reduction point. And basically, before that point, even though the quality are being declined in some lope based on the number of SSOs that is growing, but the actual quality is going down, but the visible quality is basically 100%. So on the right-hand side, we interpreted the linear quality decline in the literature into the more curved and realistic ones. And on the right, on the red axis, you can see this visible quality till quality reduction point is 100%. And before that, and people are paying full price on the supermarket and grocery store for this item. But after that, till maximum shelf life, which is basically this dashed line, the last dashed line on the right side, the supermarket should should put some sort of policy to discount this product. So if I want to make it in a mathematical equation, the quality, the sell probability will follow this formula. Basically, minimum of 1 and 1 minus shelf life divided by minus quality reduction point. It stands for probability of being on the dashed line till maximum shelf life. And if we have considered this one as sell probability, the quality loss cost will be 1 minus the probability of selling the products. And if we imagine, if we cannot sell a product, what will happen to this one? We are gonna lose the potential revenue that we can have from selling this product for the full price, which is basically this PR stands for the highest price market on the of the product. And also the food, if our food gets wasted, we need to pay the discarding cost and energy. You need to pay someone to collect this one, put it on the landfill, or transfer it into composite or anything. So 1 minus the probability of selling this one, multiply to the cost of losing the revenue and the discarding cost. So it will be the cost of the wasting the product in the system. So if we have this cost, we can easily use it in the distribution plan and combine it with the transportation cost and come up with the best plan. So let's see what will happen in the delivery, actual delivery process. So in this imaginary situation, we have two customers, customer A and customer B. Customer B has twice order as customer A, and all the other requirement, the distance to depot and everything else are identical. So imagine you are just considering the, for example, physical distance of total tour that this vehicle needs to take. It doesn't have any sort of difference. It can go to customer A, B, at first customer A on the right hand side, and then go to customer B and then return to depot. Or it can go to customer B and then visits customer A and then come back to depot. So basically the transportation cost will be the same, but what will happen to actual temperature fluctuations inside this the container of this vehicle and the quality loss that we may have. So both of customer, in both scenarios, the first customer that's been visited, customer B, will receive the product with shelf life of 278 because nothing has changed. They are just loading product from depot. They're having the imagine there's nothing is special is happening through the road, and they are both receiving the products with the same condition. So basically the temperature inside the cargo was the same, so shelf life is the same. On hour 20 on the right side of the picture, you can follow the temperature and the shelf life of the products. But the interesting thing is happening at the unloading part on the first customer. So on the left hand side, because the demand of the customer B is twice as customers A, the amount of unloading it will take from time 10 to time 15. But on the right hand side, it will take from hour 10 to hour 2 or 2.5. So we have this temperature increase for about 5 hours on left hand side, but we have about 2 hours on the right hand side. And we have this some sort of deep slope decline on the left hand side for about 5 and 6 hours. But on the right hand side, we have it about for 2 or 3 hours. So this means that even our cooling system will be able to absorb the heat even faster. And the decline on the right hand side, on the left hand side, is higher than the right hand side. And when we deliver this product to the second customer, which is basically customer A on the left-hand side and customer B on the right-hand side, the shelf life of the on the first scenario on the left-hand side is 236, but on the right-hand side 259. So on traditional distribution plan, we will not capture this sort of we will not be able to capture this sort of difference, and we will be able now we will be able to see this difference if we consider the quality loss and the food shelf life. And basically the second scenario on the right hand side is a better one, and we want to be sure that if we are considering some sort of distribution plan, we should be able to capture this sort of inefficiencies in the system in order to minimize the food waste. So we provided some sort of integrated process. I will not talk about the details of each of these modules, but we developed some sort of iterative process, which basically begins with vehicle routing. We started with vehicle routing problem with time window modules, and on the vehicle routing problem is responsible for giving us some sort of distribution plan and a routing plan for the vehicles. And the outcome of this one can be used in our temperature prediction model, which is basically will be one of the components of the quality dependent module. And this temperature will be the input of the shelf life prediction model. And as I described earlier, this shelf life can be translated in the quality cost for the plan that the vehicle routing problem has generated. And the routing plan from the vehicle routing problem can be translated into the transportation cost. And the summation of transportation cost and the quality cost will give us the distribution cost. So earlier in the literature and ordinary supply chain, most of the time they are considering just transportation cost as a distribution cost. Now we are adding the quality cost to that to have this distribution cost, and it will help us to be able to capture the inefficiencies in the system and have this food quality loss in the minimum level as possible, which is basically also economically feasible. So the result of this calculation can be shown in this picture. So this is the same scenario that I described earlier. If we have two customers, basically customer 2 has higher demand than the customer A. If our vehicle visits on the right-hand side customer 1 first and then goes to customer 2, it will be our quality dependent vehicle routing problem with time window, and the total cost will be 788 just on the summation of transportation and quality cost. But on the on picture A, if it goes to, because there is no difference on the distance that this vehicle needs to travel, on the vehicle routing problem with time window, it will be 928. So we are improving the cost by just switching the sequence of visit. And also, we captured one more thing that we were not aware of that situation earlier. If you have 3 customers and we have scenario A, we have one vehicle delivers the rational and the ordinary delivery is to, okay, go to customer 2, then 3 and 1 and come back to depot. But our quality dependent approach realized that even though the transportation costs can be higher if we use 2 vehicles, one for delivering the product to customer 2 and one to visit customer 3 and 1, but the total cost will be lower on the quality dependent approach. If you can see, the quality cost of the vehicle routing problem is much higher than the quality dependent approach, but the transportation cost on the vehicle routing problem is lower. But the summation of the total cost on the quality dependent one is lower. So we even the truck is not loaded fully, but it's recommended to have 2 trucks instead of 1 to deliver this product to the customers. So also, in order to capture the performance of the proposed approach, we used a different size of problem with different number of customers and available vehicles, and it shows that if the size of problem goes higher and higher, the gap between the quality dependent approach and the ordinary vehicle routing problem will be higher, and we will get more benefit of using this new approach. Also, we captured the we captured the impact of the food characteristic on routing decisions. So so different products have different level of sensitivity to temperature and price on the market. So it's so important to consider this 2 variables in our decisions, and it shows that the transportation cost completely dependent on these 2 variable of the food characteristics. And as main conclusions of this research, we understand that temperature inside the container of refrigerated vehicle significantly increases at the delivery point when it stops, and the high temperature elevates the growth rate of SSOs inside the food, and which means that we are losing quality. And prediction temperature and shelf life can provide an accurate estimation of food quality during distribution. And food quality loss can be converted into lost revenue and the discarding cost to be able to add as the objective of distribution plan in the cost in the form of cost. And the sequence of delivery and frequency of stops has a huge impact on the quality cost, especially when we are talking about hot weather during the summer distribution and this sort of stuff. And also, we understand the characteristic of food quality. Food can have impact on the our decision as well. So we have published at least one paper. I can just show it to you. It has more details, so feel free to reach me if you have further questions. It's a multi-objective approach model, which not only considers all this quality, cost, and everything, it also considers the emission of the vehicle, refrigerated vehicles, and also product shelf life. It's published recently in the Journal of Sustainability on MDPI publisher. And so feel free to reach out if you have any further questions. So it should be end of my presentation. So I will be happy to answer any question that you may have.